Okay, hi everyone. I think I'll take a couple of minutes to tell you about this other course, 576, in case you are interested in understanding and maybe deciding to take it in fall. So it's a continuation, it's an elective for MSPA students, and it continues on where we leave off 575. Mostly, much of the material is about basically three topics. Let me just use this part. The first topic is deep learning. I mean, it's a quite broad topic. There are so many blog posts, materials, YouTube videos that you may be coming across. But we'll actually be spending a decent amount of time, more than half the semester, on implementing some of the network architectures. So really, you will, I mean, in case even if you don't know Python, by half the semester or more than that, you will get comfortable, relatively comfortable with Python, as well as trying out deep learning architectures. So including feed-forward, convolutional, recurrent networks. So those are the ones that we'll see. We'll also look at text processing. So a couple of lectures are related to modeling text. In fact, probably one of the assignments this semester was about machine translation. So basically translating from English to Russian or something like that. Okay. The second topic in that course is what is called probabilistic graphical models. So I think somebody was asking in the forum about latent Dirichlet allocation. So it's an example of a graphical model. Okay, so graphical model is just a unifying way of thinking about many models, just like maximum likelihood estimation was a unifying way of thinking about solving for parameters or estimators, right? So so the second topic is about how to, so what are graphical models, why should I learn them, right? So they're useful for tabular data. So the type of data that we are interested in this course, graphical models are also useful for that. So we'll see why, what new things that they bring to the table. And we look at something, inference and estimation. Inference just means computing conditional probabilities and things like that. Okay. So things like, so a good application is in the medical domain. So if you see a bunch of symptoms for a patient, then those are observed random variables, and the latent states are potentially, different types of actual diseases they may have or conditions they may have. And so given the observed random variables, you want to find the conditional probability of the likelihood of them having maybe fever or something else, right? So you can find those things given a graph. Of course, even without a graph, you can do some sort of regression, but that would be considered naive. Okay. The third topic is reinforcement learning. So there's a lot of hype about self-driving cars, and you might have seen some demos of people playing video games. Not people, but computers playing video games, Flappy Bird or even Atari games. So what are the ideas behind it? They kind of let us go from just forecasting, which seems to be the central theme of this course, to forecasting and decision making. So how do both interact with each other? Okay, you take decisions, maybe sometimes you take bad decisions. That experience of taking bad decisions should be used to take better decisions in the future. So that's the rough idea in reinforcement learning and related topics. Okay, so those are the three big buckets in this course. So if you have any questions, when you're deciding about coursework, you can ask me during the break or during the next several lectures. Okay. Okay. With that, any questions about? It's not too difficult compared to what we see in this course. It's more, we are getting used to the notation, but in the other course, there's less of notation and more on handling really unstructured data, images, videos, text, things like that. So it's less mathematical relatively. More hands-on experience with Python on different algorithms or methods. Okay. Any questions about this? Okay. So let's get back to our topic. So we are already like in double-digit lecture now, 10th lecture. So we're going to continue with support vector machines. So basically, justify the name support vectors today, and then look at its. Last time when we discussed, we were really looking at just binary classification as well as just linear classifiers. So basically, a linear decision boundary, and we introduced the notion of margin, right? So today we'll look at why we can think of a nonlinear classification problem with the same machinery. Okay, so that's the kernel trick. It's actually not just used for support vector machines; it can also be used for ridge regression. Okay, so there's a kernelized version of ridge regression as well, but we'll not look at that. We'll look at kernel version of support vector machines. Okay, and next, so roughly the second part of this lecture will be switching gears. So this is pretty much the last tail end of regression or classification techniques as in supervised learning. We'll come back to unsupervised learning by the middle of this lecture and motivate. And so today's lecture will be a little bit lighter. So we'll just motivate why unsupervised learning makes sense. What are the different types of things that you could do, which you might have already done in 572, for example. And then we'll look at take a relook at association rules. So many of you might have seen association rules. So if I have time, I'll discuss a couple of ideas that use association rules, which I've used in my research in the past. Okay, if I have time. So any questions about the lay of the land or the goals for today? Okay. Okay, so as I said, first we'll revisit. The model is already specified, right? So we already said, we defined the notion of margin and wrote down an optimization problem. So it's mostly today's treatment would be mostly computational. So why, let's spend some more time with the optimization problem that we wrote down so that we can talk about support vectors eventually. So we'll spend a few more minutes on the optimization, so which means just the computation of a model. Okay, so. And the second thing would be, I guess, this is the kernel trick, and the third thing would be, I guess, unsupervised. We'll get there. Okay. So let me recap by writing down the optimization problem. It's just it's called a math program. It's just a compact way to say what you want to optimize for. Okay, your objective and your constraints. Those are the keywords people use. Okay, so what was the problem? So yeah. So this was the optimization problem. Okay, it has two terms. I just added 1/2 in the front, just to, it will be useful when we take derivatives. Okay, it's not it doesn't change anything in the first term. And in the second term was basically when we said we have non-separable data, then we will not be able to find a linear decision boundary which can separate both the classes. Remember, we are in binary classification setting, so we were allowing for some data points to cross over, and how much they cross over from the decision boundary, we're gonna capture that using this slack variable. which is there is one variable per observation, so there are n observations, right? And we're going to try to minimize. So we're going to ensure that the slacks are, slack variables are positive. That's a constraint. And actually, this is also constraint when I is equal to 1 to n constraints. And we'll have a slack budget, which is the sum of all these slacks that you're willing to provide. Ideally, if the data is suburable, all these CIs can be 0, right? So there is no need to provide any slack, and I can find a margin. I can find a linear decision boundary which can separate the two classes. Okay. So that's the second term. What is the C? C is just a balancing number. It's how to balance the two terms. It's just like in regression, ridge regression, you had to balance preference for 2 norm being small for the model as well as loss for the model. So you're balancing two terms, and if they're not in the same scale, for example, you would like to have a constant in the front. So that's this number. And so these are the two constraints. So this was the constraint that we got from thinking in terms of margin, right? And I think last time okay. So last time I had this picture of a hyperplane, beta transpose p plus beta naught is equal to 0, and p was a point here, and actually this was the p vector, and this was the x vector. Sorry, not that. That's the difference between them. X vector would be this guy, and there was a normal to this hyperplane, which was this beta vector. So everybody remembers this diagram? I mean, I just so there is a hyperplane. Think of two-dimensional plane, right? So which is what this is. So this is a plane with x1 and x2, and there's a bunch of data, bunch of data points here, maybe a bunch of other data points here. Maybe this is positive class, this is negative class. So you are, let's say there's a hyperplane like that. Then I think last time I said P is a point on the hyperplane, so it satisfies this equation. But I think last time I made a mistake. I don't know, somebody remembers, but the vector on the hyperplane, those are normal to beta. Okay. So think of 2 points, let's say P1 and P2. Then their difference is going to be a vector which will be on the hyperplane. Let's say pick another point here, P2, let's say, and this is point P1. Then the difference, think of it that as like a vector which lies on the hyperplane. That's going to be normal to beta, in the sense that beta is a vector. Okay, this vector is perpendicular to all the vectors on the hyperplane. Okay, that's all. Last time I was trying to say P is normal to beta. That's not correct. P itself is not normal to beta, but the difference between 2 points on the hyperplane, that's a vector that lies on the hyperplane. That's going to be perpendicular essentially to beta. Okay. I think he asked the question. He just came late, but anyway. So anyway, tangent. So did anybody understand what I said? Or okay, it's just a basic geometry going on. Actually, you had a question about whether P transpose beta is not 0, but so think of 2 points on the hyperplane. The difference between them is the vector which lies on the hyperplane. So that is perpendicular to beta. Okay, so their inner product is going to be 0. Anyway, so coming back to our this is our original problem, and for now we're going to actually use a tag for it, a tag as in just a name for it. I'm going to call it the primal problem, or P. Okay, short form. Okay, this is a primal objective constraint. These are technical, I guess, terminology used in optimization literature. So the problem you started with, let's just call it primal. Okay, and so before we kind of understand some more about this optimization problem, let's tease it apart. one by one. So let's understand what is the impact of C. Okay, so what is the impact of C? And in the sense, let's say C is, what's the difference between C is equal to 10 to the power minus 2 versus C is equal to 10 to the power 4, let's say, huge number. Okay, what's the difference between those two when I'm trying to find a classifier? Okay, when I'm trying to find this hyperplane which separates the two data points. Okay, two data set, two classes. So for that, let me just draw two pictures with almost the same. This is again a two-dimensional example. Two-dimensional features basically, and let's say they're the same data sets. So let's say this is C is equal to 10 to the power minus 2, C is equal to 10 to the power minus 4, 10 to the power plus 4 actually, huge number. Okay. So if the data is separated, linearly separable, what is the impact of C?
Nothing.
Yeah. Anybody else? What do you guys think? Is there an impact of C when data is separated? We said when data is separated and CIs are all 0, it can be made 0 by any hyperplane, which kind of separates them. So do you think there is only any impact of C being large or small or positive or negative? No. I mean, so the answer he already gave. So yeah, there's no impact when there is no, the data is separable. So here, let's think of the data is not separable. So maybe there's something over here. There's a bunch of data points all over the place. Maybe positive, negative, split up. Maybe this is negative here. Maybe negative here. So the impact of C being large is that it's effectively remember this. So even when the data is not separable, right? So there is a still notion of margin because we just added slacks. So there are some points which will consume the slack, as in there will be some CIs which will be positive. Yes.
To confirm, you said C is the term that you use to balance the slack, right?
Yeah. C is some number that we're balancing two terms. Anytime you have an optimization problem, think of ridge regression. Anytime you had two terms in the objective, then you'd balance it with some lambda, right? Yeah.
So does he essentially control how soft your margins are, or is that totally different?
Yeah. So that's what we're gonna discuss actually. So C is gonna influence how tight your margins have to be or how loose your margins can be. Okay. So when C is small, so you can have larger margins. So you're allowed to so although you can you're allowed to have larger margins in the sense that you're allowed to have too many points crisscrossing. You can pick a hyperplane such that there are points which are not on the same side of the margin. There could be more points because you're willing to have more slack. That you can directly see even without this graphical picture, because if C is small, then I'm willing to have many CIs positive. It's fine because the multiplier in front of them is small number. I care more about maybe this beta term being small. So I'm willing to have more points flip while choosing a hyperplane. And if more points flip, as in are not on the same side as the majority of the class, they will consume some CIs, as in CIs will be positive. I'm willing to have that. So that's roughly what I'm trying to say. So the margins are loose, and when C is large, then you kind of have to have small margins. Okay, so it's the same data. So just think of somewhere over here. Okay, so that's the effect of C. So these two hyperplanes could be different. So there will some beta 1 here, some other beta 2 here, with different different numbers actually. So in this case, whatever 2-dimensional vector, they will be different. Okay, that's the effect of increasing and decreasing C. Okay, and yeah, so that's the effect of C. Slacks, we just discussed what slack variables were. Now what we'll do is before I actually talk about so what I want to get to is what is called a Lagrange relaxation. Okay, but we have actually seen Lagrange relaxation before, so I want to just recap one example. So or I guess a Lagrangian. Okay, so what we'll try to do in the next few minutes is we wrote that original optimization problem. As I said, today's discussion is mostly about computation. So we wrote the original optimization problem. We'll try to write another optimization problem to get some interpretation, basically in terms of support vectors, essentially. But to get there, there's this device. There's this few steps that we need to take, which involve this Lagrange relaxation. And what I want to do for the next immediate minute is to discuss an example that we've already seen about Lagrange relaxation. Okay, which was in the context of how many of you guys remember EM algorithm? We did optimization. We showed that EM in its iteration improves the marginal likelihood. So marginal likelihood at the beginning of the iteration, marginal likelihood at the end of the iteration, one is smaller than the other. At the end of the iteration, the marginal likelihood is higher than the marginal likelihood at the beginning of the iteration. Okay, to do so, we kind of looked at an optimization problem, and let me revisit that optimization problem. It was like this. So we wanted to the minimize or maximize. Okay, let's see, minimize or Ri sum over I is equal to 1 to k of Qi log Ri by Qi subject to sum over I is equal to 1 to, let's say, 10. Okay, k actually Ri is equal to 1. Okay, so this is an optimization problem. This is actually the term here is called the KL divergence between R and Q. Yes, or this is just a function. This is just a function. Scale of R and Q. Just think of R and Q as vectors for us. Okay, k-dimensional vectors. So KL divergence, if you remember, was some sort of measure between two probability mass functions. Okay, so think of Ri and R and Q are two probability mass functions. So let's say k is 3, then there are 3 support probability mass functions: 0.3, 0.3, 0.4, 0.2, 0.2, 0.6, something like that. So two vectors, and you're comparing those two vectors, and the comparison is basically you input those two vectors, you get a number. This number is going to be greater than or equal to 0, it turns out. And what in the analysis of when we're showing EM does something interesting in terms of increasing marginal likelihood, we had to deal with this problem. Okay, and this problem is basically saying, okay, for Q's are fixed, their parameters or data of this optimization problem, they are not changing. Okay, and I want to change R. Can you tell me what is the R, R1, R2, R3, for example, to set so as to minimize this objective? Okay, minimize the KL divergence between R and Q. So I want to change the first parameter such that it's minimizes this distance. Okay, and of course R has to be R is not free, so there is some constraint. Okay, actually there's additional constraint, which is R is positive for I is equal to 1 to k. Okay, so these two are constraints. That's the objective, and to solve this, we wrote a Lagrangian. which is just this, right? So sum over I is equal to 1 to k qi log ri by qi plus lambda times sum over I is equal to 1 to k ri minus 1. Okay. So if you said, I mean, if you had an unconstrained optimization, as if you did not have these constraints, then what would you do? You would take the derivatives, first derivative of the objective, set it equal to 0, and hope that there is only one point where the first derivative is equal to 0, some one vector ri where first derivative is equal to 0, and hopefully at that point, since we are trying to minimize, the function is like curving upwards. Okay. Okay, so that's the second derivative. So the second derivative tells you something about whether things are curving upward or downwards at a given point. Okay, so that's what you would do if it was unconstrained. Okay, now you have a constraint which is you have many constraints actually, this and these two underlined ones, but the below one is not a big deal, because you can check whether you can be on the positive ortho, basically keep the numbers positive. Okay. But this constraint, this is called equality constraint, is something we need to work with. We cannot ignore it. So what we did is we relaxed that constraint. Okay, that's the relaxation part of. I guess that's the terminology people use when they say relaxing a constraint. They just mean you have a constraint, you have a left hand side and a right hand side. Left hand side is a sum, involves the variables involved in this optimization. Variables is also terminology. Right hand side is a number. Subtract the left hand side from the right hand side, or whatever, right hand side from the left hand side, the difference you just put it in the objective. Okay, if it's an equality constraint, it doesn't matter whether you take left minus right or right minus left. You just have something like this, and you have a multiplier. Okay, this multiplier is called a Lagrange multiplier. Okay, and now you don't have that equality constraint anymore. So now what you can do is you can take the derivatives. Okay, take the derivative and set it equal to 0, and see hopefully that you can get a single, hopefully a unique solution. Okay, so for this problem, what happens when you take the derivative? So if you take the derivative with respect to r1, what happens? So there's one term involving r1 here, and there's one term involving r1 this part, right? So of that thing is equal to q1 by r1, I guess, plus lambda r1, plus lambda is equal to, okay, this is the derivative. Okay, right? I mean, there's one term r1 times lambda, so take the derivative with respect to r1, there's lambda, and the first term is fine, right? Log of x, 1 by x, and you set it equal to 0. Okay, so this gives you r1 is equal to minus lambda, no, minus q1 by lambda. Yeah, so this is what it'll give you. So I mean, so lambda is now also a variable. Okay, it's a Lagrange multiplier, and similarly you can get it for every I. So you'll get ri is equal to minus qi by lambda, and you have the equality constraint. I mean, if you take the derivative with lambda, only the second term involves lambda, and the derivative is actually equal to the equality constraint. So you get is equal to implies equal to sum of ri minus 1, which we are setting equal to 0, which implies sum of ri is equal to 1. So that's fine. So given these two, the data is here, qi. Given these two, you can figure out what lambda is and what ri is. Okay, so how many so this is like k equations. Here's one equation, k plus 1 equations, and you have k plus 1 unknowns, which are k ri's and 1 lambda, right? So what is the solution? What is ri? So minus qi by lambda sum over I is equal to 1. So lambda is equal to, or minus lambda is equal to sum over qi, which is equal to 1, right? Or lambda is minus 1 essentially, right? And so Ri is equal to qi. Okay, so we found lambda is something and Ri is equal to qi something. Okay, in this example, so this is just an illustration to, I mean, you don't have to work it out. This is just a way to say if you had constraints, then maybe you can push the constraints into objective and take a derivative, and hopefully if you take the derivative, the equations that you get are hopefully linear. Hopefully, even if they're non-linear, they're simple. Okay, if you have a system of equations, if they're linear system of equations, you know how to solve them, you know, using linear algebra. If you don't know, if the system of equations is non-linear, then it all depends on the problem, how you can solve them. But that's a way to go. And in this case, we just got a unique solution. Ri is equal to qi. So for it is also satisfying the positivity constraint, right? So Ri has to be positive, then it's fine, right? Just as a warm up. Hopefully, are people bored? Looks like people are bored. So let's move forward. So that's the notion of Lagrange relaxation. So let's do the same for our problem. So the primal problem, right? So we're going to write the Lagrangian. So Lagrangian as a function of beta naught, xi. These are the three, I guess, primal variables. Okay. There were a couple of constraints. Remember the margin related constraint and xi's being positive. Okay. We can relax them. We can relax both sets of constraints. Although in the previous example I didn't relax the Ri's, but it's fine. You can selectively relax whichever you want. Okay. So let's use the variables alpha I and mu I to, so why alpha I and mu I? So there's going to be one multiplier per constraint. So if you remember from 3 pages ago, there are n constraints, 2n constraints. Okay, 2n constraints here. So there's going to be one multiplier per constraint, just like in the worked out example. I had one constraint, so I just had one multiplier. So I'll have 2n constraints. So let me write those. This is going to be equal to 1/2 2 norm beta square plus c times sum of I is equal to n xi. I'm going to use minus I is equal to 1 to n alpha I yi times xi transpose beta plus beta naught minus 1 plus ci. Okay, what's this? This is, yeah. And I can also use minus. As I said, okay, let me use this. I is equal to 1 to n mu I xi minus 0. Okay, so why am I using minus here? So this is a Lagrangian, and I can okay. So I have introduced 2n number of these Lagrange multipliers. Okay. So the rules for like why have a minus or a plus here just depends on what type of constraint it was. Okay. So in the previous worked out example, the constraint was an equality constraint. Sum of Ri's is equal to 1. Okay. If it's an equality constraint, it doesn't matter whether you put plus or minus. The multiplier can be whatever. It can be a real number, right? I mean, for example, in the previous worked out example, it turned out to be minus 1. That's fine. If I had put minus lambda there, it would have turned out to be plus 1. Okay. But if the constraint is an inequality, and if the inequality is of the form like left hand side greater than or equal to right hand side, then it will make sense to use a minus of alpha and alpha greater than or equal to 0. Okay, it's there is an interpretation which I will get to pretty soon, but modulo that you use a minus sign if you have an inequality which is like left hand side greater than or equal to right hand side. Okay, then you'll use a minus sign. Okay, so this is a relaxed version. Why is this? Yeah, so that's good. So similar to what we did previously, we can again take the derivative of this guy with respect to everything, all the variables involved, including Lagrange multipliers. So we can take derivative with respect to beta, derivative with respect to beta naught, I guess, derivative with respect to Xi's, derivative with respect to alpha i's, and derivative with respect to mu i's. Okay, lots of derivatives, but it's fine. I mean, the most of the terms look linear except for this guy, which is quadratic. There's some square involved. Otherwise, it's fine. So you can take derivatives. So so just like the example, let's take the derivatives, and I'm not going to work it out, but derivative with respect to beta is a vector. Okay, so it's a vector derivative that I'm doing here. If you take, actually, for let's do it for beta just for simplicity. Oops, sorry. So beta is involved here and over here, right? Those are only two places that beta is there. Everywhere else there's no beta. So the first term, if you take the derivative of the first term is nothing but beta transpose beta, right? 1/2 of beta transpose beta. If you take the derivative with respect to beta, is equal to beta. Okay, so this is vector derivative. It's a vector. It's a so you get beta, and the term that involved beta was this guy, xi transpose beta. So you can think of this whole thing multiplying beta as nu x prime I. Okay, so that you can think of alpha I times yi times xi transpose as the whole thing, something like xi x prime I, x prime I transpose. Then what you'll get is the derivative is going to be alpha I yi xi. Okay, I is equal to 1 to n. Okay, that's the derivative with respect to beta. Okay. And if you set it equal to 0, this is we're setting the gradient, I mean the first derivative of the objective function, then Lagrangian function equal to 0, then we'll get beta so here what are the variables? Y and xi are data. Okay, only alpha is not known and beta is also not known. So beta we can write, so at least there's a relation between the two variables alpha I and beta I. We don't know either of them because we have to solve the optimization problem. If we solve the first problem that I wrote in the first slide, then we get beta, so we can probably figure out alpha from there, and so on. Okay, so that's the derivative. Similarly, if you take the derivative with respect to beta naught, you will get sum of alpha I yi is equal to 0. That you can directly see from here. Beta naught is only appearing here, and so take the derivative with respect to beta naught, which is a scalar. So you just get that sum is equal to 0. Similarly, with respect to Ci, you get alpha I is equal to C minus mu I. Okay, that you can see here. One of these terms, and whose coefficient is C, and there's a Ci here whose coefficient is alpha I. So you get C and alpha, and there's there's also C with a coefficient mu. So you just pick the three terms which involves Ci, you equate them to 0. Any question?
It's
A lot. Okay, taking first, I know there are a lot of terms. I'm writing in without plugging in numbers, but we don't, we just want the derivatives and those equations. Okay, we'll just interpret them now pretty soon. Okay, so let me write down what the derivatives we got. So what is this? This is the first one. This is the second one. This is the third one, and what was it? What else? Oh yeah, and then taking the derivative with respect to alpha itself, alpha is itself, and mu is itself. We know what it is going to be. The two inequalities that we get. So yi times Oh, actually. Okay. So this was the constraint, and I think there was another constraint here. Where was the other constraint? Oh, this was the constraint. So it's fine. I mean, so these were inequalities. So let's just leave it as them as they were. So okay. So I guess 4 and 5, if needed. So what did we do with taking derivatives? We have a bunch of equations involving variables, right? We had the original variables beta naught, beta, and xi. Now we have new variables mu I and alpha I. What we're going to do is remove some variables. Okay, that's what we're going to do. And what it's going to do is change our Lagrangian, eventually get us a Lagrangian. It involves so many variables. We're going to drop a lot of variables because of these first derivatives and setting them to equal to 0, and we'll only get a function. We'll only get a Lagrangian which will only depend on alpha i's. Okay, that's what we're going to do. So basically, substitute. What did substitute what we inferred into Scriptel. So in Scriptel, if we substitute, we get sum over I is equal to 1 to n alpha I minus 1/2. I'm just writing this down. Let's not waste time on plugging it. Alpha I, alpha j, yi, yj, xi transpose xj. Okay. So we get a function once we substitute those equations, which only depends on alphas. Okay. And that you can see because mu is exactly equal to something like some offset plus alpha, so mu is gone, and beta is gone because beta is clearly a function of alpha, and the coefficient of so you can change this to something related to alpha. You can change this to something related to alpha, and xi, we just said that xi's coefficients, which involve mu and c, they just evaluate to alpha, right? So actually, sorry, they just evaluate to 0. So the coefficient in front of xi is 0. Okay. So anyway, so ultimately, what you get is a function which only involves alpha. Okay. So this involves some variables which we still haven't figured out. Okay. This turns out, we can use this as the objective of a second problem called the dual problem. Okay. So script L, which is a function of alphas only, I guess let's call it L prime. L prime, which is a function of alphas only, alpha i's. Let me all the alphas. We can use that as the objective and actually maximize over alpha values, alpha I. Okay. So we'll use that as the objective, maximize over alpha i's, subject to constraints which are alphas. Remember, we use the minus sign, so we'll get alphas. We want to keep alphas positive. That's why we use the minus sign in the Lagrangian. So we'll get the lower bound on alpha, and an upper bound on alpha is c. That's because we also wanted mu's to be positive. So both alpha is greater than or equal to 0, mu is greater than or equal to 0, and we just said alpha I is equal to c minus mu I. Okay. So if this is positive and this is positive, then alpha is upper bounded by c. Okay. So that's the constraint. So this is one constraint, I is equal to 1 to n, and the second constraint is sum of alpha I yi is equal to 0, I is equal to 1 to n. That was just the expression, this second expression here. Okay. So this is called the dual problem. Okay. So what we derived so far is we had the original SVM primal problem, we relaxed the constraints. Okay, we said, okay, let's, there are too many variables, let's take first derivatives and somehow reduce the number of variables. Okay, and luckily we were able to remove many of the variables, beta, beta naught, and xi, to get a function which only, and also mu I, to get a function which only depends on alpha I. So that's the reduction we did. Okay, and we got the function, and then we tacked on some constraints and said, let's maximize with respect to alpha I. Okay, that's okay, so that's fine. You just define another problem. So what's the relation with the original problem? Okay, because it all seems like one directional, where you did a lot of reductions, got to some objective, and so you just said, let's maximize that objective. So what's the relation between those two problems? Okay, so the relation is that so let's call this maximum value d star. Okay, this is an optimization problem. If you maximize it at some alpha values, bunch of alpha values, it will attain some number, maybe 100 units. Okay, similarly, the first problem that you had, the primal problem, let's call this p star. Okay, the objective value, whatever it achieves, the best values of beta and xi's and beta naught that we set leads to some value which is p star. Okay, now I'll state 3 facts, okay, which are something that you'll see if you did an optimization course, but this is not an optimization course. So here we're just applying some principles of optimization for our problem, which is the SVM problem. So fact 1 is a simple fact. This fact 1 can be easily checked, which is that p star is greater than or equal to d star. Okay, which means that this somehow second problem that I wrote, the best number that I can get for the second problem is always going to be lower than the best number that I can get for the first problem. The first problem I'm minimizing, the second problem I'm maximizing, but the numbers, optimal, whatever parameters I can choose, like best parameters even, I will not be able to get the second problem to have a higher objective value, it's a maximization problem, higher objective value than the first problem. Okay, this is called weak duality. And that's why I guess the second problem is called a dual problem. So there is some, I guess this is just terminology. Okay, this is called weak duality. Fact 2, p star can be equal to d star in some cases. Okay, so that's the cool part. So you have 2 optimization problems, completely different variables. Okay, there was some relation between how the, because the variables in the second problem were somehow motivated as Lagrange multipliers for the first problem. Okay, but completely different optimization problems. Objectives are different, variables are different, constraints are different, but the objective values that they'll achieve are the same. Okay, that's fact 2. It's called strong duality. Okay, this is only true for some situations. Okay, whereas the first thing is kind of true for a larger, in general it's probably true, I mean, except for some corner cases. Okay, the second equality is a really strong statement. Okay, this is actually a central point in optimization theory. Okay, it's a very core concept in optimization theory, and has a lot of applications. Okay, all the optimization scheduling and all that stuff, ad bidding, auctions in internet and all that. So they're all related to optimization problems. They kind of use this property while designing algorithms. Okay, anyway, so strong duality holds under some conditions, and for in our case, so in general, if you have a let's say the p problem was minimization over f of beta, right? Beta was that variable subject to something like g of beta greater than or equal to 0, something like this, right? Some constraint, some objective, some constraint. Strong duality holds if f is convex. Okay, convex just means something which look like a ball. Okay, if f is convex and g of beta, there is a beta for which g of beta is strictly greater than 0. Okay, which means that have a beta such that you can get that inequality, really an inequality, nothing to do with equality. Okay, and also you want G to be convex. Okay. Actually, okay, concave. G to be concave. Okay. So under these conditions, strong duality holds. Okay. Anyways, for us, it's just a fact that under some restricted conditions, strong duality holds. And fact 3 is that if strong duality holds, then something nice happens, which is that, let's say P star and D star, so there are some optimal solutions, right? So P star has optimal solution, which is, let's call it beta star, beta naught star, and Ci stars. And optimal solutions for D, let's call it alpha I star, and I guess mu I star. Stars for the best parameters that I can set to both problems. Fact 3, if strong duality, then there is some relation between the constraints. Okay, relation between the constraints, which is that alpha I star times yi xi transpose beta star plus beta naught star minus 1 plus Ci is exactly equal to 0. Okay, so that term that we added into the objective, the Lagrange relaxation, that term is exactly equal to 0 at the opt. Okay, at this value of alpha, at the values of betas, it's exactly equal to 0. Okay, so these two conditions are called complementarity conditions. So these are some facts. Okay, if strong duality holds, some conditions hold. And what are the conditions? Basically basically either the dual variable, which is alpha is 0, or the primal constraint is tight. Okay, primal constraint is just this constraint. Okay, is tight, or similarly either the primal variable is 0 or the dual constraint. Remember, alpha was less than equal to C was a constraint. So basically something to do with constraints and variables. So constraints in one problem and variables in the other problem. Some property like that holds. Okay, why is this? Why do we care about all these 3 facts, and especially the last one? It seems pretty. We need to spend more time to understand this. But the last one kind of gives us a kind of the notion about support vectors. Okay, so let me rewrite the last one without all the clutter. So alpha I yi xi transpose beta plus beta naught minus 1 plus Ci is equal to 0. Okay, so basically this equation is true. Okay, in our case, by the way, strong duality holds because of these things are true. Things are convex, things are, the constraints are nice and all that. Strong duality holds, so we can use this strong duality holds, so we can use fact 3. In fact 3, let's look at just the one of the constraints, one complementarity constraint, which is this. It basically we can interpret it as when alpha I is non-zero. Okay, let's say alpha is non-zero, then the thing inside the bracket has to be 0. Okay, because it just two numbers non-zero cannot be equal to 0. Their product cannot be equal to 0 unless one of them is equal to 0. So which means that if alpha is non-zero, then the slack condition, basically the margin condition, is tight. Tight just means that there is an equality, which means that yi times xi transpose beta plus beta naught is equal to 1 minus ci. Okay. Okay. So, and this condition is kind of the condition where so these points, these I observations, observation I, if the optimization, if I've chosen beta such that this this condition is tight, okay, there is an alpha corresponding to it which is non-zero, and that alpha being non-zero is indicative that the observation is the support vector. Okay, so that observation I for which alpha is non-zero, okay, or this slackness constraint, margin constraint is tight. Tight just means equality is it's equality, not inequality. Then that observation is called a support vector. Okay. Further, we saw from the first derivative that we took with respect to beta, beta was equal to sum over I up to 1 to n of alpha I, yi, xi. Okay, so these are all p dimensions, right? P cross 1, this is p cross 1, right? This guy. So in this summation, there will be some alpha i's which are 0, some alpha i's which are non-zero. I mean, alpha i's can take values between 0 to c. Okay. So let's look at all the alphas which are non-zero. Okay. So the alphas which are non-zero are the support vectors, as I said, and they are the only ones which determine the hyperplane. Okay, as you can see. So what is the hyperplane? The hyperplane is determined by beta and beta naught. Okay, so let's just look at beta. So beta was the sum of bunch of alpha i's times some numbers. Okay, yi is given, xi's are given, so they are not changing. All I'm saying is the support vectors, or the observations which are corresponding to support vectors, are the ones which determine beta. Okay, or these are the observations where the margin constraint is tight, and those are the ones which determine the hyperplane. And we kind of intuited about this last time, where we said points which are closer to the hyperplane that we're considering are the ones that influence the choice of the hyperplane. If I shift the hyperplane left and right, then the margin is going to change, and so some points will have a positive ci and so on. Things which are far away observations, even if I change the hyperplane, they don't need any budget, they don't need any slack, because they're already far away and they're already probably on the right side. Okay, so for those points, the constraint, the margin constraint is not tight. Okay, for those points the alpha i's are 0. Okay, the points for which the margin constraint is not tight, those are far away points. Okay, basically in terms of diagram, so if a negative point here and a positive point here, they don't matter. Okay, for this guy's alpha is equal to 0, alpha, and maybe this for this guy alpha j is equal to 0. Okay, the points which matter are extremely close to the margin. Okay, the points on the margin are the points crisscrossing, are the ones which influence the choice of the beta. Okay, that's the, I guess, naming for support vectors. Any questions? If no questions, then now let's look at, I mean, so this was just a computational exercise. I mean, model was already set up. We could have just solved the primal problem and call it a day. Okay, why did we spend so much, half an hour, let's say, to transform the problem and get the dual formulation? Is there were, of course, the interpretation of support vectors, but there's also a very important part, which is, even if you didn't understand the transformations or logic needed for the change in this to get the second problem, the second problem kind of lets us very easily tweak it to get a nonlinear model. Okay, so that's going to be the next few minutes of discussion. So getting a nonlinear model. So if you recollect, okay, let's see, beta was sum over I is equal to 1 to n alpha I yi xi, right? So we could have solved the second problem, got in some alpha I values, right? That was the variables for the second problem, and once we know the variables, we know what the model is, right? This is the model, right? This, and there is also beta naught, which I have not written. Where is beta naught? Okay, I don't have an expression for beta naught on hand, so there's also expression for beta naught. But what is f of x? F of x is beta transpose x, right? For any new point. Okay, to classify a new point, I need just to compute f of x plus beta naught. Okay, beta naught is still remaining. So if you okay, or I can write it as x transpose beta. Okay. Now this is equal to sum over I equal to 1 to n alpha I yi. These are just numbers, right? Alpha I and yi are scalars or numbers times xi transpose okay, x transpose xi, same thing. Okay, so my prediction on a new observation x is going to be just something like this. I just multiplied beta with x, right? Now if you look at the prediction, it only involves an inner product. Okay, it involves an inner product between the new data point and an existing data point, and in fact maybe all the existing data points, depends on if all the alpha is a non-zero, which is not going to be the case. But anyway, alpha is where it's non-zero, there will be a bunch of critical vectors, support vectors, and those vectors you're multiplying with the new data point to as an inner product. Okay, so instead of multiplying xi, so let's say so x transpose xi, I could also do some transformation of x transpose some transformation of xi. Okay, this is perfectly valid, right? Because I have some input raw features, I can do 100 different transformations of it, right? I mean, this is just feature engineering, I can do that, right? Which means that the whole problem, instead of thinking of x, I'm thinking of phi of x as my new x, and the whole whatever we discussed previously is still the same in the transform space. Okay, so this product is an explicit expression for phi can be made implicit by a function called the kernel function. Okay, it takes two inputs, x and xi. It's called a kernel function. Okay, so instead of explicitly me telling you what the phi is, instead of explicitly doing the feature engineering, okay, and then solving the SVM problem in this transformed space, I can say, okay, there is a phi transpose phi happening. My prediction model involves phi transpose phi. If you go back and look at this problem, this is the dual problems objective, that also involves x transpose xi transpose xj. Okay, or think of phi of xi transpose phi of xj. Right, so when I'm optimizing, I don't have to explicitly talk about phi. What I'm going to do is I'm going to talk about a kernel function, or just some black box function which takes the two x's as inputs, to two vectors as inputs, two feature vectors as inputs, and produces one number. That's what's happening, right? Whether I explicitly tell you phi or not, ultimately you're using phi to just compute one number given to two vectors, xi and xj, in the objective function or in the prediction function, right? So this common, I guess this is the function k, which takes these x vectors and produces a number, is called a kernel function. Okay, and if you use a kernel function, you're basically solving SVM in a higher dimensional space, right? For a kernel, there is a corresponding phi, right? the way I have described it. So if you solve the SVM problem, the linear binary classification problem in higher dimensions, in the original space, the decision boundary is not going to look linear. Okay, it's going to look wiggly, and we saw this for QDA, or any of we saw. Okay, I don't know if we saw this for QDA explicitly, but in the transform space, we are doing a linear classification. In the original space, that linear boundary gets untransformed and it will look wiggly. Okay, that's the intuition. Okay, and so we can do nonlinear binary classification by just specifying a kernel function. Okay, we don't even have to specify the phi function. It turns out that specifying k, the kernel function is easier. Okay, I mean, you can also always do phi and then do SVM in the transform space. That's also fine. Okay, so this transformation is called the kernel trick. Okay, okay, and as I said, instead of specifying phi, let me directly specify the k function, which takes two vectors xi and xj, let's say. And here are some examples. So if you specify xi transpose xj plus 1 to the power, let's say d, okay, d is 3, let's say. So this is an example of a kernel function. So this is k of xi comma xj. Okay, and actually for this is a polynomial. This is called a polynomial kernel. But in terms of interpretation, it's kind of simple, right? So if you just expand this out, okay, okay, d is equal to 2, let's say. So you'll get xi transpose xj the whole square plus 1 plus 2 xi transpose xj, right? And this is going to be messy, but if you expand this, you'll actually see a phi of x transpose phi of xj. Okay, this phi function will look nothing but 1 xi1 xi2 all the way to xi, that's a p, xi1 square, things of that nature. Okay, I'm not expanding it here, but if you expand the squares, you get this term. You can see that it's just okay, maybe there's a 2, or maybe to keep things symmetric, let me just keep square root 2, so that I multiply phi phi of xi transpose phi of xj is square root 2 times x, the first coordinate, square root 2 times x coordinate of the two vectors, gives you 2 times x1 xi1 times xj1. Okay, so all I'm saying is that if you expand this, you can actually interpret this as phis. Okay, but we directly wrote a kernel function. Similarly, there's some other kernel functions. Example, I think this is called the Gaussian kernel function. Example 1, example 2. This is e to the power minus some gamma times xi minus xj 2 norm square. Okay, so for this guy, it turns out that the phi function is actually huge, in the sense the number of dimensions is like infinity. Okay, but so we are not specifying that phi function, we are directly specifying the kernel function. That's the nice thing about directly talking about kernels rather than the phi functions, transformations. Whereas for polynomial, you can actually still talk about phi, but then it still has too many terms, right? Here I did not even write the terms, but there's going to be a lot of terms like this, maybe 2p or of the order of p. So these are two examples of kernel functions, and the point is that if you use kernel functions, you can just plug it into the dual optimization problem. You can solve the problem to get alphas. You can use the alphas and the kernel together. So instead, you can use the alphas and the kernel together to get the prediction, to get the classifier. Okay, alpha I, yi, kernel of x comma xi. Okay, so this is the classifier, and this classifier is going to be non-linear in the original decision space, which is the space where x's live. So if x's are 2-dimensional, so in the 2-dimensional space, the boundary will look wiggly. Okay, so that's the advantage of this dual formulation, all the computational procedure that we went through. Okay. Any questions about this part?
So every time there is a new point,
Yeah.
we kind of compute this equation, right?
Every time, so I mean, every time you have an x, you have to make, if the moment you're making prediction, your alphas. So if you solve the optimization problem, you get the alphas. That's it. And once you know the alphas, for any x test point, you can just compute this beta. Sorry, not beta, but the f of x. I mean, I dropped beta naught. Beta naught is also a function of the data points, which I don't have it offhand, so I skipped it.
So according to that, SVM becomes a parametric model, right?
It is always a parametric model. I mean, okay,
Then
so
why
you
do
mean
we
parametric
say-
model?
Why do we say that every time you just need support vectors, right, to
Yeah.
classify a new point?
Yeah, because that's what are being used here, right?
Exactly. So, but this algorithm keeps the data in memory. This doesn't delete the data, because every time when you say that you have to classify a new point, you only need support vectors and you don't need rest of the data.
Yeah, I mean, because the rest of the data is not being used in the summation, so you can drop the rest of the data if you want. So
that
any
means that computation is done only one time, or it is done every time a new point is to be classified?
No, you only do the optimization problem once. Just think of the optimization problem as equivalent to solving a lasso problem, right?
Yeah, that
Once
I
you
understand.
compress the data into beta, here I'm using the dual problem. I'm compressing the data into alphas, but alphas are not just enough. Alphas and xi is corresponding to the support vectors. Alphas, whenever they are non-zero, the x is corresponding to them, are needed because they parameterize the kernel function in my function definition.
So when you use kernel function, doesn't your you are kind of increasing the dimensions, right?
Yeah, we just interpreted having a kernel is the same as doing SVM, the linear classification, linear binary classification in higher dimensional space.
So let's say if I have a data wherein I have a lot of my feature space is really big, right?
Yeah.
I have a lot of dimensions.
Yeah.
So is it something that feature reduction is very important for SVM as compared to other algorithms if you are using kernel functions?
Feature selection, you mean?
Selection and reduction both, right?
What is reduction? It's the same thing.
Like selection. Yeah.
Okay. Feature selection is no, it's not more important, less important for SVMs. It's not.
Because in one of the other class data mining,
Yeah.
the professor said that SVM is comparatively slow as compared to other algorithms.
Slow in what sense?
Slower in terms of computation. Like it takes
Computing a model. I mean, if you know
the same amount of data.
Yeah, I mean, if you know how to solve this problem, I mean, this problem, dual problem or the primal problem fast, then you're fine, right? So this just boils down to, and then you don't have to worry about the data. So this is a pure computational issue, right? Whether you take a lot of time, do grid search to find the best parameters, or you do gradient descent to find the best parameters, or interesting methods, that's a completely different. I mean, that's like for optimization folks, or computational or numerical linear algebra folks. But they can speed it up. It's fine. Are you asking what is the complexity of solving this compared to some other methods?
I'm just saying that if you kind of compare to other algorithms like logistic regression and all.
Oh, logistic regression also, we know that we can do a gradient descent and hopefully get to the bottom.
SVM is very close to logistic regression, right? If you just modify the optimization function, it will come to logistic regression only.
We are going to comment on it very soon, but yeah, there are two optimization problems. So logistic regression, we only looked at primal as in optimization of beta, and we said just do gradient descent, we'll get to some good model. Here also you can do gradient descent. I mean, there's some constraints, of course, so it's constrained version. But if you can solve the constraint problem, you can still do gradient descent or something like that. So comparing the problems, you have to see whether the number of variables is the same, whether the number of constraints are the same, things like that. Okay, and even if they are the same, the problems, yeah, one problem could be harder than the other, because this problem, I mean, you can look at there is a quadratic term, right? Alpha I, alpha j. So it's a quadratic optimization problem. Okay, so logistic regression also has log of something, so it's not both may have, it's not easy to compare both. The number of variables here is n. Okay, number of data points is million. There will be a million variables. Logistic regression, number of features is the number of variables, so it could be smaller. But as I said, all these linear methods are still used. I mean, people talk about deep learning. Linear methods are still used because a lot of online or internet-based data sets have millions of features. Okay, you really cannot do anything beyond logistic regression or lasso basically. So if you have millions of variables, maybe you don't even have million data points, then you can probably, this problem is going to be faster than logistic regression. Yeah, so I mean that's a completely interesting question, but I can't give a definite answer. Any other questions? So the point towards the end I mentioned, so he was saying let's compare it with logistic regression. So actually let's interpret the objective. Because so far we have only been looking at binary classification, right? Binary classification. So we want to see, oh, is there any like way to use this for regression and so on. So let's kind of, now the way we wrote the original optimization problem was a completely margin perspective. Okay, we didn't think of loss functions and stuff like that. We just wanted to maximize margin, which implicitly was some sort of a loss function on some sort of a preference on what type of classifier I wanted, right? So remember the primal was 1/2 is not very critical, plus c times something, or basically sum over I is equal to 1 to n of something. What was the something? So it's basically yi times xi transpose beta plus beta naught is greater than equal to 1 minus ci, and xi greater than equal to 0, right? This is the problem. So I want to so this constraint we can write it, we can just rearrange the terms and write it as 1 minus yi of xi transpose beta plus beta naught. Okay, the same thing, I push the left hand side to the right hand side to the left hand side. Okay, and we want ci to be greater than equal to 0. That was the second constraint, right? So this guy implies this, which is the same, and the first one implies the one I wrote on the right side. Okay, so we want to, so this was a minimization problem over beta naught and xi, sorry, which means that we want to minimize xi. The second term, that wherever the xi is appearing, we want to minimize. But we have that xi has to be greater than something. Okay, we want to minimize xi, make it as close to 0 as possible. But xi has to be greater than at least 0 for sure, but it also has to be greater than something else. Okay, that something else only depends on data, the ones the arrow marks, and variables. Okay, so I can equivalently say, instead of having an explicit constraint like this, the explicit constraints like this, I can just say, instead of writing xi here, I can just say minimize the maximum of 0 and 1 minus yi xi transpose beta plus beta naught. Okay, so here, so these two equations imply xi has to be greater than equal to maximum of 0 and 1 minus yi xi transpose beta plus beta naught, right? I mean, xi is greater than a, xi is greater than b, then xi has to be greater than maximum of a and b. So if a is 10 and b is 5, then xi has to be greater than 10. If a is 0 and b is 5, then xi has to be greater than 5. So these two constraints imply this. So all I'm saying is, since we want to minimize xi, we might as well minimize directly this max of 0 comma and whatever the xi is lower bounded by. Okay, so what is this term? So max of 0 comma some number x. Okay, it's a function which looks like this. If it's a function of x. Okay, so if x is positive, then it's just the value of x itself. If x is negative, then it's 0. Okay, because if x is negative, then max of 0 and that number is going to be 0 itself. So this L-shaped thing is that function. somebody had said ReLU, so this is called rectified linear unit in deep learning parlance, but here I guess it's just called hinge function. Or it's also called ReLU, but doesn't matter. So this is the function. It's just a nonlinear function. Okay, and further, now let's look at max of 0 comma 1 minus x 1 minus z. Let me not use x because I just used x in the previous slide. So why did I want to use 1 minus z? Because actually there it's 1 minus something, right? So let me understand this even, let's delve into what we actually substituted there. It's z max of 0 comma 1 minus something else, my prediction actually, f of x, yi times f of x. So max of 0 comma 1 minus z is going to look like this. Okay, it's going to the same L, but it's flipped now. Okay, because there's a minus z here instead of x, z itself, and this point is 1 comma 0. Okay, it's basically if z is large, greater than 1, then 1 minus z is going to be negative, right? If let's say z is 2, 1 minus 2 is like minus 1 gone, so I have to be, so if z is 2 here, I better not substitute that number, but take 0 as the value at z is equal to 2. But if z is negative, then I'm fine. So 1 minus a negative number is going to be some huge positive number, and I'm just going to output that as my function output. Okay, so max of 0 comma 1 minus z looks like this. Okay, it's actually an upper bounding function. Okay, it's a function which is just above what is the misclassification function. Okay, the misclassification function looks like this z type of a thing. Okay, it's called the, I guess, the 0 1 loss function. Okay, so what is this function? It's an indicator of z less than 0. Okay, if z is less than 0, plus 1. If z is positive, minus 1. Okay, why am I calling it a 0 1 loss function? Is because in binary classification, they only four possibilities. Yeah, I mean there are 4 possibilities. That's a binary classification. Yi, so y is in 0. Y is between minus 1 and 1, and your prediction f of x is also, or sign of f of x is also between minus 1 and 1. Okay, so either your prediction is the same as y, or your prediction is not the same as y. In both cases, if it's the same as y, then y times f of x is positive. Okay, whether it's positive class or negative class doesn't matter. So if y is minus 1, you're predicting minus 1. Minus 1 times minus 1 is plus 1. Okay, so y times f of x being greater than 0 is a good situation, irrespective of whether y is a positive class or a negative class, right? And y times f of x less than 0 is a bad situation. Okay, your y is true label is negative 1, predicting plus 1. Okay, so you can think of y times f of x is like the z. Okay, so every time you're not agreeing with what the true label is, you're counting it against the classifier. So that's this misclassification. So every time, for every example that you don't agree with the prediction, you are messing up, right? So you're counting it against the classifier. So that's how you score it. So you could always find a classifier which minimizes the sum of 0 1 loss functions, sum of this misclassification errors over my training data. Instead of that, you could also minimize over functions which are like slightly above it. They look nice. Okay, this function is actually convex. Okay, this function is not. Okay, what is the consequence of a function being convex and not? Is that convex functions are slightly easier to compute with, do gradient descent and things like that, whereas non-convex functions is a little bit messy how to do gradient descent. It's not clear. Okay, you'll have to do something else. So anyway, all that is nice. So coming back to this objective, the star over here, the second term is essentially the hinge function that we just discussed in the next slide. So the second term is approximating the 0 1 loss function. I mean, just based on what we discussed. So we just said the hinge function is like, it's not approximating, but it's like upper bounding the 0 1 loss function and is convex. So this term you can interpret it as relating or relaxing the 0 1 loss function, because you see the second argument here is 1 minus y times f of x, and we just discussed 1 minus f of 1 minus we just discussed z can be substituted as y times y times f of x. So here if you substitute it, 1 minus y times f of x, right? So the second term can be interpreted as hinge loss. Okay, it's a loss function now because it's kind of upper bounding or relaxing the 0 1 loss function. And the first term you can just think of it as regularizer. So now you're back to what we started at the beginning of this course, where we had a loss function and a regularizer, right? Remember lasso or ridge regression, we had a loss function and regularizer. Here the first term is a regularizer and the second term is a hinge loss function specific to binary classification. Okay, so that's the key part. And one last thing before we take a break is, now that we interpreted this problem as minimizing a regularizer plus a loss function plus c times, I guess, hinge loss over data, right? There is a sum over I is equal to 1 to n of something, max of whatever, hinge loss over data. Now you can actually change this loss function. I mean, if we actually just change this to squared loss, we know there's this ridge regression. Okay, but there is a variant of instead of squared loss, there is a variant that is kind of attributed to support vector regression. A couple of variants or popular variants. Support. Okay, you change the hinge loss to something. What is it called? Yeah, it's called the epsilon insensitive loss. Okay, so how does the loss function look like? Loss function has to depend on f of x, my prediction, and label. It's going to be equal to 1 minus not 1 minus y minus f of x, absolute value. Okay, minus epsilon if y minus f of x absolute value is greater than epsilon and 0 otherwise. Okay, so you can extend. So mostly we have been discussing about binary classification anyway so far. The last slide is saying that, okay, since we interpreted the second term as a loss function, we can change loss functions. Of course, if we change it to square loss, we get back to ridge regression. There's a particular loss function, one example loss function that people attribute and call it a variant of support vector. They call it support vector regression. There are a couple of variants like this. It just uses loss function which is called the epsilon insensitive loss. It's basically, think of epsilon as like some number 0.01 or something, and all it's saying is if f and y, now think of regression. Okay, we want to do regression. If f of x is close to y, then I'm not going to penalize. Okay, but if f of x is not close to y, then I'm going to count it against that particular model. Okay, so in terms of diagrams, it just looks like this. So just think of this as z is equal to something like absolute value of y minus f of x. Oh no, actually, yeah, we don't need the absolute value. So think of this as epsilon width, this is z. So in this interval there is no loss. Okay, if z is like the difference between my prediction and true value, or the opposite, it doesn't matter. Either direction, if the difference is large, then I have a linear loss, linearly penalizing that model. And if it's small enough, the difference on a particular data point, I don't care, it's 0, loss is 0. So this is also convex, so like a ball, so it's relatively like a ball, so you can still optimize this compared to all the 0-1 type of losses which are bad. Okay, so if you have questions, ask me. So let's take a break for 10 minutes.